Okay, guys, it's time to do some calculations involving molarity. Molarity was defined in Solutions Podcast 2, okay? And it is the number of moles of a chemical per 1 liter of a solution. All right, so molarity is denoted with a capital M, is equal to moles over liters. And in the last podcast, I said it must be in liters. So heads up on that one. You have to convert all of your volumes into liters because that is the definition for how molarity, which is a concentration, is expressed. Okay. So if we look at this example, 1.8 molar hydrochloric acid. Well, that simply means that there are 1.8 moles of hydrochloric in 1 liter of the solution. All right. So anytime we get into any of these molarities, I always put the moles over 1 liter, and then I start my conversions or my dimensional analysis from there. So let's start with some straightforward, pretty easy examples. So first one, the average salinity, which you know is salt, of seawater is 0.60 molar. How many moles of salt are in a toy bucket containing 435 milliliters of seawater? So you see the milliliters, you see that we're asking about moles and we're given molarity. So you're going to have to make sure everything ultimately is converted into liters. Anytime you're dealing with a molar conversion and molarity, you're going to need to get everything to liters. So where you're going to start off here for your, your dimensional analysis is you could start off really with the volume and convert it over, or the molarity. And you'll see what I'm saying. There's a lot of different ways you can do these problems, and some are easier than others. Okay? So if we start with the volume of seawater, which after this example I will simply refer to as the solution, we're going to convert our milliliters into liters, and then in 1 liter, because that's the definition, right? This is the definition of a 0.60 molar solution. It means there's 0.6 moles in 1 liter of the solution, in this case, the seawater. Okay, so that's going to cancel out, leaving me with moles, and that's what we're trying to figure out here. So it is that easy. We have 0.26 moles of the salt. Now, you can also just say, all right, I'm going to take 435 in my head. I'm going to bump the decimal 3 spots to the left to give me 0.435. And then I'm going to multiply that by the molarity. All right. Let me show you something. If we rearrange this guy over here, we get this. So this is a very easy way. So if I take molarity, in this case 0.6, and I multiply it by the volume in liters, 0.435, you're going to get this exact answer. All right. Either way works, as long as you're showing your work, showing your thought process. Example 2. What volume of 3 molar hydrochloric acid should a chemist dispense to obtain 0.25 moles of hydrogen chloride? All right. So if you're feeling it, pause it, give this one a shot. Pick a somewhere to start and just go for it. Okay. In this case here, you could start with the moles of the hydrochloric. All right. If you start with the moles, then you can factor out by simply saying, and you know you need to have moles on top and then moles in the denominator. And what's the connection here? Well, it's a 3 molar solution. So in 1 liter, there are 3 moles. And that's going to get you to your unit you need, which is liters. And, you know, if it's a 3 molar, if there's 3 moles in 1 liter, and all this problem says is you need 0.25 moles, you're going to just need a fraction of that, just a small volume of that concentrated acid, okay? All right, so example 3. Here we have a saline solution, and we're being told it has a 0.154 molar sodium chloride. That's 0.15 moles in 1 liter. And we're asked how many moles of sodium chloride does it take, does a 500 milliliter bag contain? In other words, a 0.5 liter bag. So you can just do that if you'd like in your head. All right, so pause it, give it a shot, no matter which way you do it. There's more than one way, and let's check it out. Okay, so if you start with the volume, you're going to go through and you're going to do your conversions, dealing with the fact that there's 1,000 milliliters in a liter, or you can bump the decimal 3 to the left, as I already said. And then in 1 liter, in this case, that's the definition here. This is 0.154 moles of sodium chloride in 1 liter, all right? So in 1 liter, we have this many moles. What do we ask for? We're asked for moles. If you pop that in, you're good to go. Now, you can do it the other way as well. Check this out. This is simple, all right? Molarity multiplied by the volume in liters equals moles. Get the exact same answer. Whichever way you think, that works for me. However you want to approach these problems, I'm fine with that, okay? Now, in this final example, you are being asked to make a connection between molarity, the volume, and grams, okay? So a chemist wants to prepare 250 milliliters of a 1.428 molar ammonium dichromate solution from the solid chemical, all right? How many grams of ammonium dichromate are needed? Okay, so this would be like you have a scale, you have distilled water. You're going to do this. This is the real deal here. All right, so where to begin? Well, you can begin with the volume, and we've done that. So let me start somewhere else. Look at this approach. If we start rather with the molarity by saying that's 1.428 moles in 1 liter. So I'm telling you, there's many different ways you can do these, and this one works perfectly fine as well. So you have your molarity, and then you just can start factoring out. In 1 mole, here's the connection, molar mass, always the connection, and you can calculate the molar mass of this compound, and then going all the way from here to here, you can say, okay, in 1 liter, you can do that. You're just multiplying everything and dividing by everything on the bottom. There's 1,000 milliliters, okay? And you don't want 1,000 mils, all right? You want a quarter of that. So you want 250 mils, all right? So that's going to leave you with grams, and you are being asked how many grams. So the only thing we haven't canceled out here would be grams. So we're going to multiply everything on top, divide that quantity by everything on the bottom, and you're going to get 89.99 grams of ammonium dichromate. And that's going to round with 4 sig figs to exactly 90.00 grams of ammonium dichromate. Now, I want to carry this example one step further, okay? Our Georgia Standards of Excellence have us also looking at proper labeling techniques and safety. So let's use this example here. This is actually a chemical we would not be using in the school, all right? If you look here, I want to show you how you can use this to make this solutions. And that's something we will do in class constantly. You will be asked to make a standard solution from using distilled water and the actual solid chemicals. So you're going to be doing this computation, then you're actually going to grab a scale and do all this and make your own standard solutions. Okay, so here we have our scale, we have our chemical, and we have exactly 90.0 grams on an analytical balance or whatever balance you are using. And you are then going to add that to what's called a volumetric flask, okay? Now, there's a little mark here. And that mark is exactly 250 milliliters. Volumetric flasks are the most accurate way that you're going to measure these larger volumes. Now, due to the reality of our classroom, most of the time you will use graduated cylinders because volumetric flasks are very easy to knock over and they're very expensive. So the next best choice would be a graduated cylinder. Class, please do not use flasks and beakers to measure an accurate volume. You can use them for heating and mixing and those types of things and titrating and all that. But I want you to use and think what is the most accurate instrument you can use given the desired volume of fluid, of water, of whatever you're using. Okay? But in an ideal scenario, you're going to grab a volumetric flask. You're going to put your 90 grams down in here. Then you're going to add you're going to add about, please, half the desired volume. You're going to add some of the solvent to the solute. And your solvent is not always going to be water. In this case, it is. So you add you put some in. You dissolve what is here, okay? All that good stuff we talked about in the last two videos. So you get this to dissolve. Then, critical, you fill up to the line, okay? And as you can see in this image here, look, there's leftover solvent here. There's leftover water. That's because of the displacement of the solid ammonium dichromate that was put into the volumetric flask. It displaced some of it. So if you truly want 250 mils and you want that exact molarity of stock solution, it's critical that you add the compound, you dissolve it with a smaller volume of the solvent, and then you raise that level of the solvent up to the final level. Okay? All right. So, last thing, little note on safety here. This is the safety data sheet. That's what this acronym stands for, SDS, for ammonium dichromate. All right? And you can read through and get a feel for why I said we're not going to be using this one in class. But I want to talk to you about labeling stock solutions. All right? I want you to always follow these steps, whether you're making a solution for the class or your own solution to save and use in subsequent labs. All right? I want you to include the chemical name. I want you to include your name or your initials. That would be fine. How to handle it. For example, look at this label here. This is an example label for the ammonium dichromate. All right. And this corresponds with the problem we just worked out. Labeled with the concentration 1.428 molar ammonium dichromate. Hazardous. See the safety data sheet. All right. The date. Remember how we always write the date, okay? And then lastly, your initials. So these are the methods that I want you to use, and these are also the methods that are outlined in our Georgia Standards of Excellence. So now we're at a point where we're moving through a lot of these calculations, and I'm feeling like we're going to move into some mass percent molarity calculations, and my favorite, solution stoichiometry. I'll see you guys in class.